A phantom shimmered in the cosmic darkness. A star, ancient beyond comprehension, whispered a truth that should have been impossible. For decades, astronomers tracked HD 15023, a lone wanderer we now call Methuselah, and its very existence threatened to unravel the bedrock of everything we understood. Its age, by every painstaking measurement, screamed back at us, a staggering 14.5 billion years. But our universe, the grand sprawling canvas of all existence, is a mere 13.8 billion years old. How could a star be born before the very cosmos that birthed it? This isn't just an astronomical curiosity, it's a cosmic paradox, a ticking time bomb at the heart of our understanding. Our story begins not with a bang, but with a whisper from the very edge of time itself. For decades, HD 15023, a star now famously known as Methuselah, was just another dim point of light in the constellation Libra, a celestial elder unremarkable, save for its peculiar behavior. But then, the numbers started talking, and they screamed an impossible truth. Imagine a rogue, a cosmic outcast. Methuselah doesn't orbit our galactic center like a well-behaved citizen. Instead, it tears through the halo of the Milky Way, hurtling at a blistering 800,000 miles per hour, an ancient nomad on an interstellar highway. This breakneck speed was the first clue, hinting at an origin far removed from our galaxy's bustling disk. It was a star that didn't belong, a relic from a time before our galaxy truly coalesced. But its true unsettling secret lay in its very essence, its composition. When astronomers analyzed its light, they found it was almost entirely devoid of metals. That's anything heavier than hydrogen and helium in cosmic terms. Think of it like this: the universe started with only the lightest elements. Heavier elements, the stuff of planets, of OS, are forged in the fiery hearts of stars and scattered across the cosmos by colossal supernova explosions. Each new generation of stars incorporates more of these cosmic ashes, becoming richer in metals. Methuselah, however, was pristine, almost formary. It was a star built from the universe's first ingredients, a direct descendant of the Big Bang's earliest moments. This metal-poor signature was the smoking gun. It meant Methuselah was old, not just old, but ancient. And that's when the calculations began to unravel our cosmic timeline. Using established stellar models, factoring in its luminosity, its distance, its spectral signature, the numbers consistently pointed to an age of roughly 14.5 billion years. Let that sink in. A star, by all accounts, was 700 million years older than the universe itself. This wasn't a minor discrepancy. This was a cosmic violation. It sent a shockwave through the astrophysics community. The Big Bang, our most robust theory for the universe's origin and evolution, was suddenly staring down an existential threat. Had we miscalculated the age of the universe? Were our stellar evolution models fundamentally flawed? Or was there something else? Something terrifyingly simple that we were missing. The case of the star older than time had just begun, and the universe held its breath. The revelation of Methuselah's impossible age wasn't just a fascinating anomaly, it was an astrophysical emergency. Imagine a detective standing over a crime scene, all the evidence pointing to a perpetrator who couldn't possibly exist. That's where the scientific community found itself. Our cosmic clock, the meticulously calibrated timeline of the Big Bang, was suddenly out of sync. This wasn't a moment for panic, but for rigorous, obsessive reevaluation. The hunt for the truth behind Methuselah's age became a high-stakes cosmic forensics investigation. The first suspect was, naturally, the star itself. How do you measure the age of a star anyway? It's not like they come with birth certificates. Astrophysicists rely on a few crucial pieces of evidence, like cosmic detectives piecing together a profile. Firstly, there's luminosity. How bright is the star? Brighter stars burn through their fuel faster, implying a shorter lifespan. But Methuselah is a subgent, a star that's just starting to expand as it runs low on hydrogen fuel in its core. This transition phase is tricky, making precise age estimates complex. Secondly, metallicity. As we discussed, Methuselah is incredibly metal poor. Stars born early in the universe, before successive generations of stars enriched the cosmos with heavier elements, are expected to be metal poor. This was a strong indicator of extreme age, but how metal poor? Even tiny variations in these trace elements can dramatically alter a star's predicted lifespan. It's like trying to date an ancient artifact based on the purity of its gold. A slight impurity changes everything. And thirdly, distance. This is the absolute cornerstone, the cosmic measuring tape. A star's apparent brightness depends on both its intrinsic luminosity and its distance from us. If we misjudge the distance, all our age calculations go wildly off kilter. Imagine trying to guess the wattage of a light bulb if you don't know if it's across the room or across the city. For decades, the primary method for measuring stellar distances was parallax, the apparent shift of a star against background objects. As Earth orbits the Sun, it's like holding your thumb out and watching it shift against the background as you close one eye, then the other. The smaller the shift, the farther away the object. But for distant stars, this shift is minuscule, demanding incredible precision. The initial age estimates for Methuselah were based on pre-Hubble parallax measurements, which had inherent uncertainties. A small error in distance could translate into a massive error in age. It was like trying to measure the width of a human hair with a yardstick. The margin of error was simply too large for a star that was already pushing the boundaries of cosmic time. So, the scientific community mobilized. Every variable, every assumption was dragged under the microscope. Stellar evolution models, the complex theoretical frameworks that describe how stars are born, live, and die, were scrutinized. What if our understanding of how metal-poor stars burn their fuel was slightly off? What if the rate of nuclear fusion in their cores was different under conditions of extreme purity? Every single input parameter was a potential point of failure, a hidden trap in the cosmic calculations. This wasn't about disproving the star's age. It was about understanding it. It was a desperate, thrilling race against an impossible number, a fundamental challenge to our very notion of cosmic chronology. The pressure was immense. If Methuselah truly was older than the universe, then either the Big Bang model was fundamentally flawed, or our understanding of stellar physics was catastrophically incomplete. The stakes couldn't have been higher. This pursuit of cosmic truth, this relentless questioning of the impossible, is what drives us forward. If you're as captivated by these mind-bending cosmic mysteries as I am, smash that like button and subscribe. You won't want to miss what we uncover next. The Cosmic Forensics team, composed of astronomers and astrophysicists from around the globe, converged on Methuselah. The problem was clear. The existing data, while the best available, carried too much uncertainty, especially in that critical distance measurement. This wasn't a time for incremental improvements. It was a call for a quantum leap in observational precision. Enter the Hubble Space Telescope. Perched above Earth's blurring atmosphere, Hubble offered an unparalleled vantage point, a sharper eye on the universe than anything before it. Its mission was to deliver the most precise parallax measurement ever achieved for Methuselah. For a decade, from 2003 to 2013, a team led by Howard Bond at Penn State meticulously observed HD 130283. Imagine pointing a telescope at a tiny distant pinprick of light and tracking its infinitesimal wobble over 10 years across billions of miles of space. It was a testament to human ingenuity and patience. The results from Hubble were the first true breakthrough. The new parallax measurement provided a significantly more accurate distance to Methuselah, pinning it down with far less uncertainty than ever before. This was the linchpin, the piece of evidence that would begin to unravel the paradox. A more accurate distance directly translated into a more accurate intrinsic luminosity, which in turn allowed for a much tighter constraint on its age. But distance alone wasn't enough. The second crucial piece of the puzzle involved refining our understanding of Methuselah's incredibly low metallicity. Remember, stars that are metal poor burn their fuel differently. They are more efficient, consuming their hydrogen at a slightly slower rate than their metal-rich cousins. This means they live longer. The challenge was quantifying exactly how much longer. Scientists pored over the complex equations of stellar evolution, running sophisticated computer simulations. They incorporated new data from theoretical models that better accounted for the physics of these primordial stars, tweaking parameters like the precise ratio of helium to hydrogen from the early universe. One key insight came from understanding the oxygen content within Methuselah. Oxygen, though a metal in astronomical terms, behaves uniquely in stellar interiors compared to other heavier elements. By analyzing the faint spectral lines of oxygen in Methuselah's light, scientists could refine the star's initial composition with unprecedented accuracy. This wasn't just about the presence or absence of metals, it was about the specific ratio of different heavy elements, which subtly influences the star's internal structure and, crucially, its rate of fuel consumption. These combined efforts, the surgical precision of Hubble's distance measurement, and the painstaking refinement of stellar evolution models based on Methuselah's unique chemical fingerprint, began to close the gap. The initial 14.5 billion years age estimate started to shrink, slowly, agonizingly, but surely. The impossible number was being reined in, forced back into the cosmic timeline. It was a scientific tightrope walk. Every decimal point mattered. Every theoretical nuance became critical. The age started to drop, 14.0 billion years, then 13.9 billion. The universe's accepted age of 13.8 billion years loomed, a cosmic wall they were still perilously close to hitting. The tension was palpable. Had they finally found the truth, or was the universe still playing its most audacious trick? The breakthrough evidence was in, but the verdict was still hanging by a thread. After years of meticulous observation and relentless calculation, the cosmic verdict on Methuselah was finally delivered. The data from Hubble, combined with the refined stellar evolution models and a deeper understanding of the star's unique metallicity, converged on a new, more precise age, 14.27 billion years, with an uncertainty of plus or minus 0.8 billion years. Let that sink in. The initial, impossible, 14.5 billion years had been wrestled down. The new estimate, still incredibly ancient, now placed Methuselah's age within the bounds of cosmic possibility, albeit at the very edge. The star was no longer older than the universe, but it was still almost as old. It was a close shave, a cosmic near miss that left scientists exhilarated and humbled. This wasn't just about a single star. It was a profound stress test for the very foundations of modern cosmology. Methuselah became the universe's ultimate cosmic clock, a benchmark that forced scientists to re-examine the precision of everything. Firstly, it provided a powerful validation for the Big Bang model. The fact that our most ancient known star, after rigorous reanalysis, could be reconciled with the universe's age was a massive victory. It meant our understanding of cosmic expansion, the initial conditions of the universe, and the rate at which it has aged was remarkably accurate. Methuselah didn't break the Big Bang, it sharpened its edges, confirming its robustness even under extreme pressure. Secondly, it pushed the boundaries of stellar evolution theory. The detailed study of Methuselah's incredibly metal-poor composition forced astrophysicists to refine their models for how these first-generation stars burn and evolve. It was a rare opportunity to study a star that emerged from the universe's primordial soup, offering direct insights into the earliest stellar processes. The minor adjustments to the models, though seemingly small, were crucial in bringing the star's age into alignment. It showed that while our models were largely correct, there was always room for greater precision, especially at the extremes of cosmic age and composition. Think of it as tuning a cosmic instrument. Before Methuselah, our understanding of the universe's age and stellar lifetimes was like a well-tuned piano, but Methuselah was a rogue note, threatening to throw the entire symphony into discord. By painstakingly adjusting our instruments, the telescopes, the equations, the theoretical models, we brought that note into perfect harmony. The slight adjustments to the rate of cosmic expansion, the fine-tuning of the Hubble constant, the precise calibration of stellar luminosity across different metal contents, all these intricate pieces were brought into sharper focus because of this one star. The Methuselah star wasn't a cosmic anomaly that disproved our universe. It was a cosmic Rosetta Stone that helped us read its oldest chapters with greater clarity. It stood as a silent, ancient sentinel, a living testament to the universe's earliest moments, its existence pushing humanity to achieve unprecedented levels of scientific precision. It was a terrifying challenge that ultimately strengthened our cosmic clock, proving that our understanding of time itself on the grandest scale was remarkably sound. The Methuselah star, HD 1.0283, stands as a testament not to a cosmic error, but to the incredible, self-correcting power of science. It was a paradox that screamed at us from the deepest past, a celestial mistake that forced us to question everything. But instead of shattering our understanding, it strengthened it, pushing the limits of our observational capabilities and refining the very models that describe the universe's life cycle. These impossible objects aren't glitches, they are cosmic challenges, signposts demanding deeper investigation. They remind us that the universe is not a perfectly understood textbook, but an ongoing, thrilling mystery. Every time we encounter something that defies our expectations, it's not a failure, but an invitation to learn more, to push harder, to see beyond our current horizon. The relentless pursuit of these anomalies is the engine of discovery, the very heartbeat of scientific progress. The Methuselah star, ancient beyond measure, reminds us that the quest for knowledge is itself an eternal journey, always refining, always expanding, always reaching for the next impossible truth. Tell me what you liked or disliked about this video. What do you think could be changed to make it better? I read every comment and will respond to every suggestion.